This is Free Range Digital Design Foundation Modeling, Chapter 15. So we finally arrived at the point where we'll be doing primarily design, and this is modular design. What we're going to do in this chapter is review some of our design approaches and then give an overview of the digital design process, at least the overview as I see it. Till now, we've been using primarily brute force design for our circuits, although we did design one circuit using iterative modular design. Brute force design was very straightforward, but it was very limited because it was a tabular based format and the number of rows in the table was related to the number of inputs in the circuit. So as your circuit had more inputs, had more rows in the table, and certainly anything more than 4 inputs, which is a 16-row table, is just not overly feasible. One of the circuits we designed was using iterative modular design, which is the ripple carry adder. Now this kind of overcame the number of inputs problem, but it was very limited in the number of circuits it can design. And we'll see some other couple circuits using iterative modular design in later chapters, but it too is really limited. So where we want to end up is with modular design, and that's a very efficient design approach, and that's what we're spending most of the time in this text. Modular design is inherently done with black box diagrams, which indicate what modules you're using. So this is the highest level of abstraction, and generally speaking we stay there at that high level of abstraction when we can, simply to be as efficient as possible. We will need to drop down to lower levels, but generally speaking you want to stay at a high level. So modular design, a couple rules here just to start off with. When you're drawing these black box diagrams, the goal is to be clear and concise. Readability is important, perfection is certainly not as important, essentially because perfection generally takes a while longer. Now, if you're drawing these by hand, you just make them neat. If you're drawing them with some type of computer software, once again you make it neat also, and certainly drawing it with computer software doesn't mean it's going to be neat and concise and all those things. So idea, make it clear and concise, very readable, and that way it can transfer information to the reader as quickly as possible. Inevitably, you're going to get to parts of your design that you're trying to document with a picture such that you don't know what to do, so you have to make something up. In those cases, what you need to do is state what assumptions your drawing is going to make or your design is going to make. Nothing against stating assumptions, certainly if it helps clarify your drawing or make your drawing more efficient, etc., etc. Part of the documentation process is what your black box diagram is you need to label everything. Something unlabeled is essentially leaves it up to the reader to figure out what that is, which essentially makes it an unknown because they may not assume the right thing. Label everything. Oftentimes you try to use standard modules, in our case foundation modules, but it doesn't always work. So if you have to define your own module, or if you have to use your own module in a diagram, you have to make sure you define that somewhere so the person reading your diagram knows what it is. For example, if you toss a ripple carry adder into your diagram, everyone knows what that is. But if you have a mystery box, you have to define what that mystery box does. Digital design is modular design, and what we're going to do is try to use as many modules as we can. It makes for efficient designs. Certainly you don't want to reinvent the wheel. That's going to make your design process less efficient. And what we're charged with doing here is using the modules that we know as we know them. So if they're changed in any sort of way, you essentially have to redefine it. You have to provide a definition of that module. So let's look at these examples here. So this example looks like an OR gate, but it has 2 outputs on this thing. It may be a valid circuit, but it is no circuit that I know about. So if you use something like that in your diagram, you have to define it. So here is a ripple carry adder. Check this out, labeled properly RCA, that it uses bus bars, 4 bits wide, that matches the width of the sum, as a carry out. Everything looks good on this thing. There's a question of whether it needs a carry in or not, And so here's the same circuit with a carry-in, but this circuit is okay. It's assuming this circuit doesn't have a carry-in, which may be what you want or not want. Certainly if you need a carry-in, it has to be there. This circuit actually lists the carry-in. These are both valid circuits. They reflect what I know about ripple carry adders. Here's a circuit that looks like a ripple carry adder, but it's a mystery because I know ripple carry adders generally have bus inputs here. This one doesn't. When you read this, you think, did the person make a mistake and not put the bus bars in there, or did this person really want a 1-bit ripple carry adder? If the person wanted 1 bit, the better idea would be to use a full adder rather than a ripple carry adder. This is not a good circuit either. It should be, if it was drawn correctly, it should be a full adder. So here we have another circuit. It says adder, but I don't know what an adder is. I know what a ripple carry adder is, or an RCA. I'm not sure what an adder is. In this case, this is not good as listed. If you were to use this, you'd have to define it somewhere. But these are valid boxes here. All the other boxes are not valid to use in your diagram without an explanation. So I tried to list a set of rules describing the design process or the design methodology. These are extremely arbitrary. What you'll find is, as you do these problems, you will develop your own style, and that's what I encourage you to do. This is just some rules to plop it out there to get you going on this stuff. So certainly, first thing you want to do is read the problem. Essentially read the problem and understand it, because that's going to lead to drawing the top-level black box diagram. So this is just a black box that shows the inputs and outputs of the diagram, which certainly absolutely should be able to do from any problem description. If I can't draw this top-level black box diagram, something's wrong. The problem's not properly defined. So next thing I want to do is look at the problem and decide what kind of submodules I need in that diagram to make the circuit work. For instance, the submodules we know about right now, essentially a ripple carry adder. So what that means to me, anytime I see a circuit that needs to add something, I know it needs a ripple carry adder. We'll revisit that as we go along. So once you plop down all your modules, what you want to do is connect all the modules. So that means connect the modules to each other and connect the modules to the inputs and outputs. If you happen to use a non-standard module, you need to define it somewhere in your diagram. I encourage you to use as many foundation modules as you can, because everyone knows how those work and you don't need to define them. Anytime you have to stop and define something, it's going to take extra time. Anytime you have to implement something in hardware, it's going to take extra time to test it. So you want to try to use as many pre-used modules as possible. You've completed your black box diagram, top levels, lower levels, and so what do you need to do? Go on to the next problem? No, you need to take a look at it. The design process is not linear. You're not going to start from the beginning and get to the end, or at least I never do that. I make mistakes along the way, but I always try to look at the final product and try to catch those mistakes, and that's what you need to do also. Now, it could be a mistake in incorrect circuit. It could be something you forgot to label. Either way, you need to fix it. Looking at your diagrams, everything needs a label, including the top level black box diagram. It needs a name. Certainly the name should be self-commenting in nature and not too long. Make sure all the modules are connected, particularly the inputs are connected. So if there's an input that's not connected, that's considered a problem. Every input needs a connection. The outputs you can leave hanging. They don't necessarily need connections. A lot of signals need appropriate labels. Now, not every signal needs a label, but all the signals that are important to your diagram, you should label those signals. All the bundle width should be indicated with the bus bar, which is a bus bar, and it should have a number sitting there like that. All the bundles should be marked and include a width with them. Make sure all the lower level modules have labels also, so we know what they are, and make sure that you only use standard modules, or if you use a non-standard module, you provide a model for it. And lastly is we come to Mealy's fifth law of digital design. You should model all circuits using many smaller level modules rather than one big large top level module. Essentially, you're going to need to to test this thing. Having a lot of small modules makes it more testable. Additionally, you want to reuse as many previous modules as you can. If you make some giant module, reinventing the wheel, it's not an efficient design process, certainly not as efficient as reusing previous modules.